as we continue through our voyage through the learning process of learning the C programming language, we are now at a stage where we need to start looking into some of the more detailed programming constructs. What I mean by programming constructs is some of the terms, the syntax, the structures that are used in order to define the various parts of a program. And in this session, we will be looking at a few different important constructs. One is called control flow, another one relates to functions, and we will also talk a little bit about the scope, concept of scope, and how it applies to variables and how they need to be interpreted. So, an outline of what we will be covering over here. I will first start by talking about a topic that has been the subject of a lot of discussion from nearly 4 or 5 decades ago, and essentially relates to this topic called structured programming. At the time it was introduced, it was sort of a completely new way of thinking about how programs are to be constructed, and there was some good theoretical background in terms of what it can and cannot achieve, and there were good reasons for why programming languages should be structured in a particular way, or rather programs should be structured in a particular way, and what kind of support programming languages should provide to do so. Nowadays, of course, things have moved a little bit beyond that, but the broad ideas of structured programming are still very relevant and important for us to understand and know. Having done that, we will then go into some specifics more related to the C programming language. And in all of these topics, what I will do is I will be first looking at some kind of generic background in terms of what the control structure or the programming structure is about, and then go into the specifics of how it looks in a language, in the C programming language, right. And for that we will be using specific programming examples like and those will be run on the Replit programming environment. So the first of those would be control flow, where we will look at various kinds of conditional and iterative kind of structures. Then we will look at functions. What do we mean by functions? What does it mean to declare, to define a function? What are the arguments? What are the results? How do we get data in and out of a function, and so on. And finally, we will look at one topic which is interesting from the practical point of view of programming. This is not so much in terms of the pure structure of the program itself, but it has a lot of impact on how we interpret the presence or use of variables within parts of a program, and it is called scope. So let us start by looking at the topic of structured programming and try and understand a little bit about what role that had to play in the development of the C programming language. I am going to start by discussing something which those of you who have done any prior programming courses would already be familiar with. For those of you who are not familiar, this is something which I am not going to go into in a whole lot of detail in this course. I will be talking about it at a fairly intuitive and superficial level, and part of the reason for that is in this course we will not directly be using flowcharts, but on the other hand the concept of a flowchart, what is it, why is it useful, is very good to know. Right? So in order to motivate what is a flowchart and sort of take you through the development of a flowchart, I am going to use this example of a quadratic equation solver, right. And in this case what we have is a quadratic equation is essentially defined using 3 inputs, which in this term we will call A, B and C, and in this case I am going to just add in one extra input right over here, and the reason for that will become obvious in a moment. The reason is that at any given point in time, this function or program that I am writing in order to solve quadratic equations, I am going to assume that it can only return one value, it can only give me one value, right. But we know that a quadratic equation has 2 roots, right, which are specified mathematically as minus b plus or minus square root of b square minus 4ac divided by 2a. So what I am going to do is use this select as an input, which basically selects between these two, and what I will say is that I will use the plus option if select is equal to 1, or oops, this is an error, of course this should be minus, right. So minus b minus square root of b square minus 4ac divided by 2a if select is equal to 2, okay. So this essentially sort of defines our problem, right. We have certain inputs we have certain expected outputs, and we know that this is a pure mathematical computation that we can just perform, right. We assume that our computer that is available to us is capable of performing these operations, namely multiplication, subtraction, addition, square root and division, right. Those of you who again have prior programming experience might be aware that square root is not usually a native function of most processors, but that is okay. We have ways by which we can compute square root. So, I am going to assume for now that yes, there is some magical way by which you can compute the square root. Okay. So, now if I sort of go through this, right, now the question that I have to ask is, alright, what should I do, how do I go about solving this problem? Okay. And we are going to draw a flowchart for this purpose, and as you will see over here, there will be a lot of standardized symbols that I use, right. For example, this oval is used in order to indicate the start of a flowchart, okay. And unfortunately, in my opinion, a lot of the sort of documentation or literature around flowcharts seems to lay a lot of stress on what kind of symbol you use for what kind of operation, right. So, if you have an oval, then it has to be for the start, or it has to be a circle, or it has to be a rectangle or a square or a trapezium or a parallelogram. The point is that is actually secondary, right. There is a reason why those conventions were used, because on relatively large flowcharts it makes it easy to identify where you have conditions, where you have input or output, where you have just processing or computation being performed and so on, right. So, in this case I will try and stick to the standard symbols as far as possible, but like I said, the main point to keep in mind over here is not so much what symbols are used, but rather the process by which we construct the flowchart. Okay. So, keep in mind that all of these symbols are conventions, right. There is nothing fundamentally mathematically grounded over there which tells you that these are the only symbols that you should use for these purposes. The whole point is that by using these symbols we ensure that we are able to communicate with others and they are able to understand our flowchart more easily. Alright, with that out of the way, I start my flowchart by having an ellipse over there with the word start in it. Okay. What do I do next? I need to get my inputs, okay, and I assume that I have some kind of ability to read data, right, and typically this parallelogram is the symbol that is used in order to indicate A, B, C, or rather to indicate IO, input or output, right. And here what I do is I just give a statement over there saying read A, B, C and select. I do not specify where to read it from, I do not specify whether it is from a file, from a keyboard, from text to speech conversion or speech to text conversion where somebody says something and it is converted into numbers. We do not care, we just need to get those values. Once we have them, what do we do with them? We perform a computation, right, and here I have introduced a new temporary value d, right, and I say d is equal to b square minus 4ac. Now, why did I do that? Because there is one catch in this solution that I have over here, namely that if b square minus 4ac is negative, I need to be careful. It means that my solution is going to become a complex number, right. I need to take a square root of a negative number, which is basically an imaginary value. I do not want to deal with imaginary values right now, right. So, what I am going to do is, if I perform a condition check, right. So, this diamond shape that we have over here is a condition check, and in this case what is checking is whether d is less than 0, okay. If d is equal to 0, we do not care, that is perfectly fine, right. But if d is less than 0, I need to do something, and if d is greater than or equal to 0, I need to do something else, okay. So, I have now created two branches, right. So, you can already see that there is a divergence in which path I might take through this program at this point. The first thing that I can say is, if d is less than 0, I print some kind of an error message. Most likely I will say I do not know how to handle complex numbers. And now after this I actually have a choice. The way that I have drawn it is, I assume that I am going back to start, okay. Instead, what is more likely is that I would actually probably have just come to a termination and said, okay, this is the end of the program, right, to a stop condition, okay. There are different ways of looking at flowcharts. It depends on what you want your system to do. If you want your program to continuously sit in a loop and wait for inputs, then it would proceed this way. The one catch with the way that I have written it is that in principle this program is never going to terminate, right? It does not have a stopping condition, right? It always says prints an error message and goes back here, right? And as we will see, the other messages also end up going back to start. That is one way of doing it, ideally not, right? The other preferable method would have been that after printing the error message it actually stops. If you wanted to actually rerun the program, what we would say is after you have stopped this particular run through the program, you would need to go back and once again restart, and that would be a completely different invocation of the program, so to say. Okay. But for the time being, I have used this approach where I basically say that I just print an error message and go back to start. Once again, like I said, the going back to start or going to the end of the program is a secondary part. What matters over here is this portion, right, where I say that I am checking a condition, and based on the condition either I would go in this direction, right, towards the printing error message, or I would go down, right, and continue with the flow of the program, right. So these terms that I am using, the flow of the program, the control which says which of these branches is being taken, right, all of those are terms which are best explained by example, right. So rather than trying to say what I mean by the flow of the program, by looking at this example you should get an idea that the sequence in which I am going through these steps is what I mean by that flow. Now anyway, the thing is, assuming that d is greater than or equal to 0, that is the n condition is satisfied over here, I need to check one more condition. What is that condition? I know that at least I can find the roots of the equation, there is no problem there. But now I need to know which one is being asked for. Am I asking for the first root or the second root? And if I find that select is equal to 1, right, I need to do something, and if its select is not equal to 1, I need to do something else, right. Okay, so if select is equal to 1, what I am going to do is I am going to print out the first root and once again in this case go back to start, or I should have gone to a stopping condition, right, either one of those is okay. And the alternative also has to be filled out. Clearly I still have one unhandled branch, so what I do is I consider the select equal to 2 case. If select was equal to 2, then I print the second root, and after that I basically go back once again this way, right. I am sort of merging branches out here, right. So this dot over here basically indicates that both of these follow the same path, right, and they are essentially from this point onwards they are the same, right. Physically it does not matter whether I join here or whether I was to join it here or whether I was to have a completely different line and have it join over here, they are all the same. And the final part, right, the only branch that had not been handled so far was what if select is neither equal to 1 nor equal to 2. Once again I do not know what you are asking for, right, you are asking me for a root which is neither the first root nor the second root, it does not have anything else, print an error message and go back, okay. So this in other words gives us a possible way of running through all the steps required in order to solve this problem, right. And as you can see, there are a few terms that we can identify and observe here, right. One of them is this notion of control. Control basically says what is the sequence in which operations need to be performed. First I need to start, then I need to get my inputs, then I need to perform one preliminary computation, then perform one check. If that does not fail, go to the next check. If that is also not there, go to the next check. Based on the results of any one of these checks, I might end up going to another branch and so on, okay. So the control in other words gives me the operation, and it basically what it does is it captures the flow of operations that we are performing during our computation, right. The flow is basically the sequence or the order in which we are performing those operations, right. So when I say that something indicates a control flow, that is what I mean. There is a set of operations that need to be performed and the control flow specifies the order or the sequence in which those operations need to be performed. And the crucial thing that you can see over here is that there is this notion of branching, right. What I mean by branching is there is this first diamond out here has two different branches, one going in this direction, the other one going down. The second diamond once again has two branches, one going out to this side, the other going down, and the last diamond also has two branches. The reason they have two branches is in all cases they have been broken down into yes or no, true or false kind of conditions, right? And typically flowcharts try and break everything down into true or false conditions. In principle, it's possible to have flowcharts that have more, but the very structure of that diamond shape is usually oriented more towards a true-false kind of a split, right? And if you want to have a more complicated branching, you typically split it into a sequence of true-false conditions. Now, there is a reason for that. One of them is related to the fact that this is trying to in some sense mimic what the hardware can do, right? And typically what hardware is good at, we have already looked at the basic idea of what machine language or assembly language would look like. There can be so called branching statements, right? And branching statements in hardware are essentially going to compare one condition, and if the condition is true, do something. If the condition is not true, just continue along the path that you were earlier following, okay, or potentially branch somewhere else, okay. So, this notion of simplified branching, where we basically break everything up into just diamonds with yes no kind of conditions, allows us to mimic what is going to happen in hardware and to capture the control flow very accurately in terms of a flowchart, okay. Now, flowcharts like this are very useful because they help in the thought process, right? They basically allow you to take a problem that you know and break it down into steps that fall very closely or follow very closely with what a computer is capable of doing, right? Having said that, the larger that your program gets, the more difficult it becomes to draw meaningful flowcharts, right? And even with fairly complicated algorithms, it starts to become more and more cumbersome to start drawing flowcharts. One is because they are a visual form of communication, they are not a very dense or compact way of communicating information, right. So, very often what you will see instead of flowcharts is what is called pseudocode, right. So, pseudocode is the other option that is used instead of flowcharts. Once again, it's not directly a replacement, they each serve their own purpose. Flowcharts allow you to capture the overall branching and other things very easily and in a manner that's easy for anyone to just look at and grasp in a quick way, right. Whereas pseudocode is meant more for sort of capturing all the set of computations that you have one after the other. And in order to interpret pseudocode, you probably need to have a little bit more familiarity with some kind of programming to start with, right. So, flowchart is probably the best way to get started for an absolute beginner to programming, but once you have some level of familiarity with it, it probably makes more sense to think more in terms of pseudocode and build up your program by basically breaking it up into something which is neither assembly language nor a syntactically accurate language like C, but somewhere in between, which sort of breaks things down into steps that a computer can follow, but without worrying too much about the syntax or whether your notations and your semicolons are correct and so on. Yeah. So, this notion of a flowchart essentially is one form of something called a control flow graph, right. And a control flow graph is, as the name suggests, it's basically the term graph over here is used in the context of graph theory, which is a branch of computer science which studies the connections between different kinds of objects, right. And a control flow graph is essentially something like a flowchart, right, which basically says there are certain computations or tasks that need to be performed, and there are connections between them which basically specify the order in which those tasks need to be performed, right. A flowchart is sort of a restricted or a specific subset of a type of control flow graph. And there was a theorem that was first discussed in 1966 by Bohm and Jacopini, which essentially said that you could use a restricted subset of control flow graphs where you sort of made sure that the only kinds of operations that are allowed in those control flow graphs are restricted to a specific subset of different types of operations, right. And that even with these restrictions, you can basically perform any computation that could be performed by any computer, right. The mathematical sort of terminology used for this is to say that a computation is said to be tractable or possible if it can be computed on something called a Turing machine, right. And effectively what we are saying is, if something is Turing computable, that is it can be run on a Turing machine, we consider it to be computable. Right. Now the details of Turing machines, Turing computability and so on are way beyond the scope of what we need to do in this course. They are very interesting topics, fascinating topics on their own, right, but you do not need to know them in order to do programming, right. Why they are relevant for us is because this theorem was able to show that by having a very specific form of control flow graph, you can basically model anything that any other computer in principle, in theory, can do, right. And that restricted subset essentially consisted of 3 types of operations. The first was called sequencing, right, and by sequence what we say is you have a concept of a statement which you can think of as one basic operation that you need to perform, right. If I want to add 1 to a number, that is a statement, right. On the other hand, I could also have a sequence of statements: add 1 to A, subtract 3 from B, multiply A and B and put the result in C. Those are 3 different statements, but I am going to think of the combination or the sequence of those 3 also as one complex statement or a sub-program, if you will. Okay. So they define this concept of a sequence of statements as constituting something called a sub-program, and they said in addition to having this ability to have sequences of statements, you need to have 2 other kinds of operations, right. One is called selection, where as you proceed through the program, you can choose between 2 different sub-programs based on some condition. So selection essentially means that at some point I might have to decide whether to continue with the sub-program that I am currently at, or whether to switch over to another sub-program and do something else. And the third step over there is something called iteration, right. Iteration or iteration, as it is sometimes pronounced, effectively says I need to take a particular set of statements, a sub-program, and repeat it as long as some condition is satisfied, right. So this notion of iteration, selection and sequence, right, were shown to be sufficient for any kind of computation, right. Now why this theorem was important was because up to that point people were used to programming in assembly language. In assembly language, as we have already seen, you basically have branch statements, and in branch statements the simplest way to implement a branching statement in most of the programming languages of the time was to use something called a go-to statement, right, which literally was as good as saying, hey, put this address into the program counter and jump there and start executing instructions. Okay. So a go-to is very explicit, it basically is very closely matching with what the computer hardware sees, right. It allows you to control exactly what you are going to see in terms of the machine code that gets generated. The problem is it's entirely possible to start having programs where you have go-tos all over the place, right, just branching from one place to another and rapidly becoming nearly impossible to understand, right. So there was like growing discontent among people at that time, basically saying that, look, there are programs being written that are essentially impossible to understand because of the way that go-tos are being used over here, to the point where there was a very influential paper that came out by a computer scientist by the name of Edgar Dijkstra. Essentially the title of this paper was "Go-to Statement Considered Harmful," right, essentially saying that the use of go-tos was a bad idea and it should be avoided in programming. What structured programming tried to do was to sort of eliminate the go-to statement, right. It said that rather than just having arbitrary go-tos, I will only be able to select between 2 possible options, or I will be able to loop over a certain set of instructions or statements, right. And it turned out this was good enough for what was needed, right. Now what does that mean for us, right? The important thing is that had an impact on the development of programming languages way down the line, right. Pretty much any programming language that came after these theories and after these concepts were well studied apply at least some of the concepts of structured programming, right, and they one of the things is it makes multiple languages sort of mutually recognizable. If you know one language, it is relatively easy to understand another language, right, and the differences come more in sort of the syntax and what sort of primitive operations or basic structures they provide you to work with, right. These three stages, the sequence, right, is essentially the ability to group statements together, and in pretty much all programming languages this translated into something called the basic programming block, right. What I mean by a block is a group of statements one after the other. In some languages this also was called subroutines. In C, as we will see later, it essentially led to the concept of functions, right, or rather it was implemented using the concept of functions. There is also the concept of just programming blocks in C, but functions are probably the main place where this idea of sequencing and reusing different parts of a subprogram are implemented. It also brings up something which is sort of a side effect. It is not a direct requirement for structured programming, but this whole idea of the scope of a variable is something that comes out as a result of this subprogram concept that we have brought in from looking at sequences of statements. Okay. The next thing that structured programming required was this idea of selection, right, and this is essentially just saying, okay, we need to have the ability to conditionally execute different blocks of code, right. A block is already defined out here. If I have two different blocks and I need to choose between them, there should be some mechanism in the language that allows me to choose between two blocks. That essentially led in the C programming language to if else and switch case kind of constructs, which we will look at later. And finally, the concept of iteration, which is essentially repeated execution, right, and we sort of distinguish between iteration and selection because iteration is a very common construct and has very specific uses. It is repeating the same block of code multiple times. Now in principle, iteration can of course be implemented using selection by repeatedly branching back to the start of that, but it makes more sense to actually think explicitly in terms of iterating over a certain block of code multiple times, which is why it is treated as a separate concept in structured programming, right. And in the C programming language, of course, what that does is it leads us to constructs such as for and while. All of these are different programming constructs that we will look at in a lot more detail and try and understand. The reason why it's good to sort of have a little bit of this background is because it gives you context to understand why these things were developed the way they were, and hopefully that will also help you to use them the way that they are meant to be used.